Hello everyone, welcome back to this online class. I am Francis Okech and my YouTube channel is Professor Francis Okech. Today we are going to look at Calculus 2 and our topic is u-substitution based on the definition of integration as the reverse process of differentiation. Remember, so far we've looked at power rule and u-substitution, yes, that reduces to power rule. But now, what about the u-substitution that is based on the definition of integration? And under this topic, we are going to look at some forms of integrals. The first one is integral of the form where the integrand is f prime of x over f of x. So how do you go about such kind of integrals? So what you do here, you write let u be equal to our denominator, which is f of x. This is the kind of substitution that you need to make when you have integrals of the form f prime of x over f of x dx. It's like what you have in the numerator is the derivative of the function in the denominator. So in this case, you let u to be f of x. And every time you make a substitution, you must find the derivative. So this means that du dx is equals to f prime of x. Or it means that if I cross multiply, I will have du to be equal to f prime of x dx. So that is the substitution. Whenever you make a substitution, you must also find the corresponding differential. So we are going to substitute that. So what will be our integral now? It will now reduce to the integral of, remember this is now du over u. Because we are saying f prime of x dx, that is the same as du. And f of x the same as u. You can write this as the integral of 1 over u du. Now you need to ask yourself, what did you differentiate to get 1 over u? It was the natural log of u. It is ln u that when you differentiate, you get 1 over u. Now there's a constant c of integration. And so if you replace u, you need to get your answer as equal to ln, instead of u, we are going to write f of x plus a constant c of integration. So what is important is knowing where to start from. Which substitution do you need to make? That whenever you have such kind of integrals, you start by saying let u be equal to the denominator. I'll give you some examples on this kind of integrals. And the first one is when we have, you can write examples. You write examples. You can be asked to evaluate these integrals. The first one is the integral of x minus 3 of x squared minus 6x plus 2. Dx. So you're going to say let u be x squared minus 6x plus 2. So in this case, it means that our du dx, when you differentiate, you get 2x minus 6, which is the same as 2 into x minus 3. So from here, you can make dx the subject. It means that our dx will be equal to du over 2 into x minus 3. So those are the substitutions. Let me bracket them. The first one is that u is equals to the denominator, which is x squared minus 6x plus 2. And another one is the differential dx, how will it be? It will be du over 2 into x minus 3. So when I substitute into our integral, we'll now get x minus 3. Now the denominator is u times dx, which you have said to be du over 2 into x minus 3. So you see here, the x minus 3 will cancel with this other x minus 3. So we'll have the integral of du over 2u. And you see 1 over 2, you can factor that out so that we have 1 over u du, which when you integrate, you get 1 over 2 ln u plus a constant c. And that is our answer, but we have to replace u. So you check where we have defined our u. And if you look at here, our u is x squared minus 6x plus 2. So this answer can as well be written as 1 over 2 ln x squared minus 6x plus 2, then plus a constant c of integration. That is very simple. Another one is the integral of tan x. How do you go about it? Part B is how to integrate tan x dx. Remember that this can be written as the integral, because tan x is the same as sin x over cos x. Tan x is equals to sin x over cos x. You can write it here. You can write a note that when we talk of tan x, it is the same as sin x over cos x. So this is very important. Very, very important. So because now we have expressed tan x as a fraction or a rational function, you can now say that let u be the denominator, that is cos x. So what about du dx? Du dx will be equal to negative sin x. You can make dx the subject. Dx is equals to negative, or simply I can talk of du over negative sin x. So let me bracket these substitutions. U is equals to cos x, and another one is dx is equals to du over negative sin x. So if I substitute into my integral, I'll get this, the integral of sin x over u dx is du over negative sin x. So you realize that sin x will cancel with the other one, so that we have the opposite negative is outside, integral of 1 over u du, which is negative ln u plus a constant c. And you also know that from the laws of logarithms, you also need to take note that if I have m times log a, this can also be written as log of a raised to m. That again is very important. This is the third law of logarithms. I want to apply this so that my answer can as well be written as the log ln of u raised to negative 1 plus c, which you can as well write as ln of 1 over u plus c. So if you replace u, what do we get? u is equals to cos x. So this is the same as ln of 1 over cos x plus c. But what is 1 over cos x? Is the same as sec x. So ln of sec x plus a constant c. So what you need to take note of is that if you differentiate tan, not differentiate but the integral, so you can take note that the integral of tan x with respect to x should always give us ln of sec x plus a constant c. That is what is important, and we are going to circle this one or bracket it. This formula you can also find in your ISMP table, the integral of tan x. You see how we have derived it using the u-substitution method. We'll also look at the integral of cot x. Integral of cot x. Let me write it down. But C, we want to integrate cot x with respect to x. So how do we go about this? You need to rewrite cot x. Remember again that when we talk of cot x, it is the same as 1 over tan x. But we said tan x is sine x over cos x. So 1 over tan x will be equal to cos x over sine x. Again, that is very important. Why am I doing this? Because I want to express cot x as a rational function, so that this integral can now be written as is the integral of cos x over sine x dx. And so once we are there, you let u be equal to sine x. So when you differentiate, you get du dx, derivative of sine x, that is cos x. And so you can make dx the subject. That means dx is equals to du over cos x. So let me bracket the substitutions. We have u is equals to sine x, very important. And another one is dx is equals to du over cos x. As I told you previously, that every time you make a substitution, you must also find the corresponding differential. You find the derivative. So what will our integral look like? It will now be the integral of cos x over u. And instead of dx, I'll write du over cos x. So you see we have cos x in the numerator. There's another cos x in the denominator. So what happens is that the cos x will cancel out. This will cancel with this, so that our integral is the integral of 1 over u du, which you can write as ln u plus a constant c. If you replace u, that will give you ln, what was our u? That was sine x, ln of sine x plus c. So what you need to take note of, that when you integrate cot x, you need to get ln of sine x. You need to take note of that, therefore the integral of cot x dx is the same as natural log of sine x plus a constant c. Also very important formula that you can find in your ISMP table. Another one is, how do you integrate sec x? This was part E, not E, but C. So part D, we write the integral of sec x dx. So how do you integrate it? This is what you need to do. We are going to say let, even before, because I need to know what I should substitute as u. So the first thing you need to do is you rewrite the integral so that you multiply both numerator and denominator by sec x plus tan x, so that we'll have the integral of sec x, then we are multiplying by sec x plus tan x in the numerator. Do the same to the denominator. We're also multiplying by sec x plus tan x dx, so that in our numerator it can be written as, if I open the bracket, it will be the integral of sec x or sec squared x plus sec x tan x over denominator, which is sec x plus tan x. Then there's dx. So you see, why am I doing that? Because I need a rational function. So from here it is easy to see what should be u and what should be du. So you can say let u be equal to sec x plus tan x. That is the substitution. So this one you have to differentiate it. You find du dx. So this means that du dx, what will it be equal to? When you differentiate sec x, you get sec x times tan x. When you differentiate tan x, you get sec squared x. Or you can say that if I make dx the subject, it is the same as du over sec x tan x plus sec squared x. So back to our integral. Therefore, we now talk of the integral of, let me use a different color, the integral of sec squared x plus sec x tan x, and everything now, you see denominator is now u, and instead of dx we have that as du over sec x tan x plus sec squared x. So look at our integrand. You can see there's sec squared x plus sec x tan x. The same thing is in the denominator. So the whole of this one, let me use a bracket, the whole of this will cancel with this. So those two will cancel, can simplify, so that our integral will now be the integral of 1 over u du, which is the same as ln u plus c. But what is u? Replace it, so this is the same as ln of sec x plus tan x, then plus a constant c. So what you take note of is the integral of sec x dx should give you natural log or ln of sec x plus tan x, and then you add a constant c of integration. So this again is a formula that is available in your SMP table. Take note of that formula, very important. And lastly, let's look at the integral of cosec x. So I'll call that part, let's say part E. How do you integrate cosec x dx? So again, you rewrite this one. Excuse me. How do we rewrite this integral? Now I am going to multiply numerator and denominator by cosec x plus cot x, so that this integral can be written as cosec x times cosec x plus cot x. We are multiplying by that. Do the same to the denominator. It will be over cosec x plus cot x dx. And you can now open the bracket in the numerator so that we have the integral of cosec squared x plus cosec x cot x, everything over cosec that is cosec x plus cot x dx. So now you see we have a rational function, and so it is easy to know what you need to let to be u. So let u to be the denominator, that is cosec x plus cot x. So that is our substitution. Now let's find the derivative. What is du dx? So you can say this, that this means that our du dx is the same as, when you differentiate cosec, you get negative cosec x times cot x. And what about when you differentiate cot x? You get negative cosec squared x. And so you can make dx the subject. From here, it means that dx is equals to du over, let me factor out the negative. So I have negative, that will be negative cosec x cot x, negative cosec x cot x, then plus cosec squared x. So that's what we have as the differential dx, or the differential of x. So let me bracket this one. That's also very important. Now we substitute in this integral. What will you get? So you can say, therefore, we now talk of it's now the integral of cosec squared x plus cosec x, cosec x times cot. This should be cot. Let me rewrite it. Cot x. So that is cot x. Denominator, that was u. Then times dx, which is du, over negative cosec x times cot x plus cosec squared of x. So look at our integrand. what do you realize? That there's some factor that is common in both numerator and denominator. And so it will cancel out. It is this one here, it is common. So the all of this will cancel out with this. So we remain with the integral of -1 over u du, which is the same as negative ln u plus a constant c. And this can now be written as, when you replace u, you can now write this as negative ln, instead of u, we write cosec x plus cot x, then plus a constant c of integration. So what you need to take note of is that the integral of cosec x dx should always give you negative natural log of cosec x plus cot x, then plus a constant c of integration. So again, this formula is very important. You see, these formulas, you will need them when you are doing ordinary differential equations. You will need to apply these techniques of integration in solving ODEs and even PDEs. So this marks the end of today's lesson. Thank you all for watching, and don't forget to subscribe to my channel, and that is Professor Francis Gage. Also, don't forget to share, you like, and comment. Bye-bye.